Hello again, class. This is Chapter 7-6, Number Systems. It is the last lesson in Chapter 7. And we are going to be working with several different number systems. The first one is the decimal system. Well, that's the one we use. And our number system is actually based on powers of 10. In case you're wondering, well, how does this relate to working with all these exponents that we've had? Just a reminder of our place values that we have ones, which is 10 to the 0, tens, which is 10 to the first power, hundreds, which is 10 to the second, thousands, 10,000s, 100,000s, and millions, as I have written here. So let's look at a number such as 287. Now this is a little different. We don't often think about this. But if I think of 287, I can think of 200 plus 80 plus 7. Now, if I write that into what we used to call expanded form, that's going to give me 2 times 10, 2 times 100, plus 8 times 10, plus 7 times 1. Now, if I use the powers of 10, that I wrote up here, we have 7 times 10 to the 0, because 10 to the 0 is 1. Any number raised to the 0 is 1. 8 times 10, that gives me 80, because 10 to the first is 10. And then 2 times 10 to the second, because 2 to the second, 10 to the second is going to be 100, and 2 times 100 is my 200. Now, in our decimal system, I have a limited number of numerals that I can use, or digits that I can use. The only digits that I use in our decimal system is 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. There is something called a binary system. And this is kind of the basis of computer language. The binary system is also called base 2. It only uses the digits 0 and 1, and all the place values are based on powers of 2. So, 2 to the 0 is going to relate to a 1. 2 to the first power is going to be a 2. 2 to the second power is going to be a 4. 2 to the third power is an 8. 2 to the fourth power is a 16. 2 to the fifth power is a 32. And 2 to the sixth power is a 64. So instead of using one, I still use ones because anything raised to the 0 power is 1. But instead of using a 10, I'm going to think of it in terms of a 2. That third place value, instead of 100, I'm going to think of a 4. Okay? Let's look at what happens if I see a number in base 2, and I want to put it into our decimal system, or what we call base 10. Now you'll notice that there is a subscript of 2. And we usually don't write a subscript for our base 10 or our decimal system, but we do write a subscript for every other number system that we use. Okay, let's start in here. 1, 0, 0. A 1 means I have that place value. A 0 means I don't have that place value. Don't get thinking that this is 100 in base 2. This is 1, 0, 0 in base 2. My first place value right here is supposed to be a 1. The 0 says you don't have any of those. My second place value is supposed to be a 2. I don't have a 2. My third place value up here is a 4. This says you have one of those. So how do I figure out the decimal value? I have a 4 plus nothing plus nothing If I add them up, I get 4. So the binary number 100 in base 2 actually equals the decimal number of 4. Hit pause and see if you can figure out B. Would you come up with a decimal value of 25? This says you have a 1. You don't have any 2s. You don't have any 4s. You do have an 8. You do have a 16. And when I add them up, I get 25. So what happens if we don't have one of these table things? Because you can't go around making a table for everything. I write these numbers above the digits that I have. This is a 1, a 2, a 4, an 8, and a 16. So I take 16 plus 8 plus 4. I skip the zeros because they're just going to be 0 anyway. And then I add them up. 16 plus 8 is 24, plus 4 is 28. Or you can think of it as 4 plus 8 is 12, and 12 and 16 is 28. Let's look at D. The first place value is a 1, the second is a 2, the third is a 4. 4 plus 2 plus 1 equals, yes, 7. You try E. Did you get 20? Were some of you even able to do it in your head? Let's say that we're going to change a binary number. Whoops, this isn't worded right. There should be a decimal number to a binary number. Now, just a reminder, we have 1s, 2s, 4s, 8s, 16s, 32s, and 64s. So I'm going to look at 9. I need to find the largest place value that is still less than 9. Well, that's the 8. That's 8, or 2 to the third. What's left? 9 minus 8 is 1. So can I still use the 4? No. Can I still use the 2? No. Can I use the 1? Yes. So I am going to need a 1 in the 2 to the third position and another 1 in the 2 to the 0 position. Since I don't have 2 to the second or 2 to the first, I'm going to put zeros there. So 9 is going to be 1, 0, 0, 1, base 2. Don't forget your subscript. Think about it. This is 1, this is 2, this is 4, this is 8. Add 8 plus 1 is 9. Let's look at 16. Now, if I think to myself, all right, I have 1s, 2s, 4s, 8s, I have 16s. That's my 2 to the 4th. If I have a 2 to the 4th, that's 16. I'll use 1. I don't have 2 to the 3rd. I don't have 2 to the 2nd. I don't have 2 to the 1st. I don't have 2 to the 0. And remember, I'm in base 2. Let's see if you can figure out D, C and D. How'd you do? Did you get them right? Did you remember to put your subscript for base 2? Now, all the other number systems that we ever work with are going to be very similar. You're always going to be working with the powers. If the base is 5, that means I can use the digits 0, 1, 2, 3, and 4. And my place values are going to be 5 to the 0, which is 1, 5 to the first power, which is a 5, and 5 to the second power, which is 25. If I'm going to place this, take this number in base 5 and put it into decimal value, I have 2, I have 1, I have 0. 2 times 25 gives me 50. 1 times 1 gives me 1. My value for 201 in base 5 is going to be 51. Okay, again, we don't always make tables. So we have 1s, we have 5s, we have 25s when we are in base 5. So I have 25 and 1, that gives me 26. I can also work in base 6. Again, 6 to the 0 is 1, 6 to the first is 6, 6 to the second is 36 because 6 times 6 is 36. I have 0 in the 1s, 0 in the 6s, 1 in the 36. So 100 base 6 equals 36. You hit pause and try D. And I hope you got 83. And that concludes our lesson for Chapter 7-6. Please reply with watermelons. Scouting out.